Hi, everyone. I wanted to provide a walkthrough on the exam 3 review worksheet. So let's go ahead and start with that, and we'll just walk through this. And of course, if you have questions, definitely continue to reach out. So first of all, we're just going to walk through some definitions. I think it's important to repeat these and think about them. So I'll provide a little bit of narration on that, and then we'll walk through some examples and likely walk through what I've assigned to you too to help make that clearer and easier for you. So first of all, the estimated standard error is an estimate of the standard deviation of a sampling distribution of the sample means selected from a population with an unknown variance. It is an estimate of the standard error or standard distance that the sample means deviate from the value of the population mean stated in the null hypothesis. The t statistic, known as t observed or t obtained, that is an inferential statistic where you draw meaning from it, used to determine the number of standard deviations in a t distribution that a sample mean deviates from the mean value or mean difference stated in the null hypothesis. The t distribution, or student's t, is a normal-like distribution with greater variability in the tails than a normal distribution because the sample variance is substituted for the population variance to estimate the standard error in this distribution. The degrees of freedom for a t distribution are equal to the degrees of freedom for sample variance for a given sample n-1. Each t distribution is associated with specific degrees of freedom. As sample size increases, the degrees of freedom also increase. Some FYI stuff. The degrees of freedom for a t distribution are equal to the degrees of freedom for a sample variance n-1. The t table lists values for 6 levels of significance for 1 and 2-tailed tests. 3 assumptions for a 1-sample test are normality, random sampling, and independence. Some more definitions. The 1-sample t-test is a sample statistical procedure used to compare a mean value measured in a sample to a known value in a population. It is specifically used to test hypotheses concerning the mean in a single population with an unknown variance. Example number 1. Social functioning is the ability for an individual to interact or adapt in a normal or usual way in social environments. This area of research is of interest to behavioral researchers, particularly in the medical or clinical settings, and those who study human development. As an example for the use of a 1-sample t-test, Albert et al. 2007 asked if relatives of patients with their obsessive compulsive disorder, OCD, are as healthy as those in the general healthy population. In their study, they recorded the social functioning of the relatives of patients with OCD using a 36-item short-form health survey, SF6, with scores ranging from 0, worst possible health, to 100, best possible health. They cited that the mean social functioning score in the general healthy population of interest was 77.43. Using a sample data set that approximates their findings, we will test whether the mean score in the sample data given below significantly differs from that in the general population of 0.05 level of significance. So here are our scores. You may want to put these in Excel. For what I'm going to walk you through, you don't necessarily have to do that, but putting stuff in Excel a lot of times can help. So first, we're going to start with stating our hypotheses. So let's break that down and walk through that. First, state the hypotheses. The population mean is 77.43, and we are testing whether it is equal or not equal to the population mean, which differs from the sample mean. Therefore, the null hypothesis is that the mean is equal to 77.43. The interpretation or the inferential statistics on that means that for relatives who care for patients with OCD, the mean social functioning score is 77.43, the same as that in the general healthy population. Your alternative hypothesis is that for relatives who care for patients with OCD, the mean social functioning score is not equal to 77.3. Step 2, set the criteria for a decision. The level of significance for this test is 0.05. We are computing a 2-tailed test with n-1 degrees of freedom. With n equals 18, the degrees of freedom for this test are 18 minus 1, which is 17. To locate the critical values, we look in the unit normal table and go to Appendix C. So we look in the unit normal table, okay? And that was previously posted right there in Brightspace for you under where these recordings are, unit normal table, in Appendix C. and go to the column for the 0.05 proportion of the two tails combined. The critical values, and please, as we're walking through this, take a moment and find this in the table so that it makes sense to you. The critical values are plus or minus 21.10. For a graphical representation of this, and I use a lot of resources here when I lecture about stats. I use our textbook, other stats textbooks. So that's really just a note from me so that I can draw that for you on the whiteboard here. So for a graphical representation of what we are doing, we can look at drawing it kind of like this, what that should look like in terms of your overall sketch, in terms of what we're actually trying to identify, should look something like this. Let's grab our whiteboard. And what that looks like is like, so here's our whiteboard right here. Okay. And what we're doing is we're setting the criteria, for a decision. Okay. And what we're trying to figure out here in terms of our test, this is a two-tailed test. What we have is we have, our normal bell curve right here. Okay. And then we have basically like our scale right here. And then sort of the middle, we have 0. And that's going to go to the left or right. And we have -1, -2. And then a little bit further, a little bit past -2 and beyond, because of that 2.110, this right here. And remember, it's at the spot or beyond. That is going to be our rejection region. And that's a two-tailed test because we're going to look at both tails. So this is your rejection region for your -2.110 rejection. And this is where we're going to reject. It's rejection region, okay? Region, or you're going to, basically what this means is you're going to reject the null hypothesis, okay? Reject the null hypothesis. And I think I can probably make this a little bit bigger here for everybody. And then we're going to have 1, 2, and then the same thing, just a little before 2, well, before we get to like 3, okay? It's the same thing here, -3, -4, etc. We're going to have this other rejection region right here for the other part of the tail. Remember, if it's at there or beyond, you reject it. Everything inside here is when you retain the null hypothesis. And remember, when we're talking about the null hypothesis, there's 2 different ways to write it, of course. So you want to have our a null hypothesis, like I have in my worksheet. This is your null hypothesis, okay? And this is typically your alternative hypothesis. This is null, and this is alternative in terms of how we write that and the notation. So that's what we're trying to identify. So what we're trying to figure out, again, is that obtained value versus that critical value. So what we have first is we always start, remember, with our critical value. Then we're going to do the math and figure out the critical value. So moving on, let's go back to our worksheet here. So we just did this. This is our whiteboard example, okay? This is our whiteboard example we just did. And the shaded regions represent the rejection regions with the critical values plus or minus equal to 2.110 for the T distribution with degrees of freedom is equal to 17. Like I just mentioned, if the value of the test statistic falls in the shaded region, we reject the null hypothesis. Otherwise, we retain the null hypothesis. We will compare the value of the test statistic with these critical values. If the value of the test statistic is beyond a critical value, either greater or less than plus or minus 2.110, there is less than a 5% chance we would obtain that outcome if the null hypothesis were correct. So we'll reject the null hypothesis, otherwise we retain the null hypothesis. So next we're going to compute the test statistic. So in this example, we compute the sample mean and the standard deviation for the data in the above table. So the sum of all scores is your mean, which is 62. And as we talked about in the past, to compute the standard deviation, first subtract and square the difference of each score from the sample mean, and then divide by n-1, and then take the square root. which is 2094. So I believe, give me just a second, I might even have this Excel sheet so I can show you. Let me see if I have that handy. All right, so I don't have that, but it's okay. What I'm going to do, guys, ladies, is I'm going to walk you through the steps here, and then we're going to do the example step by step so that it makes sense. So just think about the steps, and then we'll do the steps together on the other one, on the other problems here, okay? So we're going to we compute the standard deviation for subtract and square the difference of each score from the sample mean, and then divide by n-1, and then take the square root, which is your 20.94. We will then compare the sample mean to the population mean stated in the null hypothesis, 77.43. To find the t-statistic, we first compute the estimated standard error. To compute the estimated standard error, which is the denominator of the t-statistic, we divide the sample standard deviation, SD, by the square root of the sample size, or n. In this sample, standard deviation is equal to 20.94 and n is equal to 18. Therefore, the sample error is equal to the standard deviation divided by the square root of n, which is 20.94. Therefore, the standard deviation is divided by the square root of 18 is 4.94. We're going to find the t-statistic by substituting the values of the sample mean, m equals 62, the population mean stated in the null hypothesis, which is 77.43. And the estimated standard error we just calculated. So the estimated standard error is 4.94. The t obtained value is the mean minus the sample mean divided by the standard error. So that's 62 minus 77.3 divided by 4.94 is negative 3.126. Step 4, make a decision to decide to retain or to reject or retain the null hypothesis. We compare the obtained value negative 3.126 to the critical values. Because this falls beyond the critical value in the lower tail on the left-hand side, it falls into the rejection region. The decision is to reject the null hypothesis. So what I'm talking about is this right here. So it was negative 3.126, and this was negative. That's your rejection region on your left-hand side. So now, using the following formulas, we're going to do the same steps right here to walk through this. But because I think putting this in Excel would make it easy, we'll do that. So, all right, so let's explain the sample a little bit more. So if we go back to our desktop too, so the first thing we talk about is what we need to do is we need to do each step. So let's start with step 1 with our new set of data, okay? So this will actually all be the same because we have the same, we're going to use the mean of the healthy population, HELTHY, against our sample, okay? So our step 1 is we're just going to say that it's equal to or not equal to. That's the first part of showing our work. Just same hypotheses. The population is 77.43, and we are testing whether or not the population differs from the sample mean. Null hypothesis, it's the same. Alternative hypothesis is not. Now, the next thing that we got to do is we need to set the criteria for this decision. Again, that's the same. The level of significance is 0.05. We're computing the two-tailed test with n-1 degrees of freedom. So the critical value is going to be exactly the same. So it's exactly what we just looked up for step 2, because the number of values did not change. It's still 18. So the degrees of freedom is still 17. So that's literally the same exact steps here, going back to our unit normal table, same critical value. Now it starts to get different when we start to look at our sample here. So the first thing we talk about is computing the test statistic. And I feel like this is where it might get more complicated, or maybe folks might get stuck. So I'm going to show you with Excel what we're doing here. So first, the sample mean is the sum of all scores, and then we divide, right? So let's take a look at that. So this is the social functioning scores in the second set of data. So it's this, and we divided it. I actually just told Excel to give me the average, but it's the same as taking 1088 divided by 18, because there's 18 values. That's where that comes from. Now, the next thing we're going to do is we're going to take the difference of the scores and the sample mean. So we're taking this right here, 17, from each value and subtracting this right here, which is our I-21, okay? So we're I labeled this mean, so I just said subtract each value minus the mean. So 17 minus this, so on and so forth. So each one of these is minus the mean, which is this number right here, okay? So 17 minus this mean, 44 minus this mean, and so on. Then I took and I square the values. So negative 43.444 is equal to this. Now, we probably could make us have a few less decimals or a few more, but usually it's better to maybe put it down to like 2 decimals across the board. So we might just, you got to do them one at a time though. So that's too many. So usually I would go down to 2 decimals, okay? So just do that across the board like that. So these numbers aren't so gigantic. So just 2, it's too many. Like that. So all we're doing is we're just making these smaller, okay? Letting them round, etc. with Excel, okay? Because otherwise the numbers are just too gigantic to, well, just, we don't need to go that many places really, okay? And it's the same thing with these. I mean, these all really could be like that, realistically. That's the sort of the raw data, all those decimals. We don't really need to have all of these decimals. So we're just gonna go like that and like that and so on with all these. Now I think it might be possible. Yeah, I can just go like that and make them all small, just highlight that. It's kind of the same thing, okay? And then this, of course, same thing. And this, of course, same thing. This, of course, same thing. And this, of course, same thing. Now, I'll talk about these numbers in a moment. So all I did is I took and I squared every one of these values like that. Then I did my sum of my squares, which was right here. This was my sum of all the squares. As simple as it sounds, you square values and you sum them, you get the sum of the squares. Then I took and I divided this to get our variance, and I divided it by n, this minus n minus 1. Well, clearly there's 18 values, so n minus 1 is 17, so our degrees of freedom is 17. So I divided this by that, and then I took the square root of the variance, which was this, and I just told it square root of K21, which is our 20.17. So now if we go back into our Word document, that's 20.17. So very similar with our values here. And then take the square root, which is 20.17. So then the next thing we're going to do is we go back up here and let's just look at this. So in this example, it was the standard deviation was 20.17. N was also 18. So we're going to do this formula, but we're going to divide it by the square root of 18, and it's going to be slightly different. It's not going to be the same. It's just going to vary a little bit different because the data happens to be very similar. So if we go like that, so we need to get the standard error, we take our standard deviation of 20.17 divided by the square root of 18. So we can go back to Excel and we can do square root of 18 right here. Hang on. Equals square root of 18. There's our number. Okay. So that's going to be very, very similar to what we had before. Well, it's actually the same one because it's the same amount of values. Okay. So then we're going to take this number and divide it by that number, because that is literally our square root of 18. So 2017 divided by 4.24. So that's going to be equal to, this is L21, that divided by M21, that one. And we're going to get a very similar number because, like I said, our data happens to be similar. So we'll make that again So 4.75. Okay, so if we go back to our Word document. So we do all of this in terms of showing our work. Where was that? Okay, so this is 20.17. And then this is 4.75. Okay, so now we have our standard error. Should be pretty straightforward, hopefully. If you have questions, shoot me a text, send me an email. So we got this. Now we need to figure out our T obtained value. So it's going to be the M. Remember, that's like against our critical value. The mean minus the sample mean divided by the standard error is what we're going to do. So this is our formula that we're going to do right here. So we're going to go like this and like that. And then we need to put that in. So that is going to be equal to the 77.43 minus our sample mean, but we have that. Our sample mean is 60.44, so a little different. So we go back to this minus 60.44 divided by our standard error, which is 4.75. So we can do that pretty easily. We just go, let's go 77.43. And we can just take and go equals L12, that number, minus 60.44. Let's do our numerator first, which is I22, sorry, no, 21. And then we're going to take this number, 16.99, and we're going to divide it by, this equals M12 divided by this number, which is our 4.75, which is N21. And we get 3.5722. Of course, we can make these smaller, 3.57. So that is our new T obtained value, 3.57. So now 3.57, does that matter? Why is that relevant? Well, we got our T obtained value, which is 3.57. And what was our critical value again? I think it happened to be 2.110. So because we have 3.57, in this case, it does exceed the critical value, but on the other tail. And when I say the other tail, I mean to the right. So we just calculated that out, but in this time we went to the other tail. So this is over here. So again, we're going to reject the null hypothesis for our decision. So that's the same thing, but that's our last step. Make a decision because T is equal to 3.57. It does still fall beyond the critical value, but not in the lower tail. It falls below the critical example in the upper tail. So that one's a little bit different in terms of if we're going to retain or reject the null hypothesis. So in this case, T obtained value is equal to 3.57. And because 3.57 falls beyond the critical value in the upper tail, which is the one to the right, upper tail, it falls in the rejection region. The decision is reject the null hypothesis. Next, the T table lists critical values for T distributions with various degrees of freedom. The T statistic for a one sample T test is the difference between the sample mean and the population mean as stated by the null hypothesis divided by the standard error. The sample standard error is used to estimate the population standard deviation and the estimated Cohen's d formula. An estimated Cohen's d formula is a measure of effect size in terms of the number of standard deviations that the mean will shift above or below the below the population mean stated by the null hypothesis. The larger the value estimated by Cohen's d, the larger the effect in the population. The proportion of variance is a measure of effect size in terms of the proportion or percent of variability in a dependent variable that can be explained or accounted for by a treatment. In hypothesis testing, a treatment is any unique characteristic or sample of any unique way that a researcher treats the sample. The formula for Cohen's d is the following: the mean minus standard deviation, the mean minus the sample mean over the standard deviation. Well, we have that 62 minus 72.43 divided by 20.94 is equal to 0.74. So now calculate the same steps for the second set of data that I gave you. Please show your work. So now in this case, n is equal to 20. So we're going to want to look at these social functioning scores a little bit differently. Was that 18? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So these are new scores, which should be a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this one's different. This is 20. So we're going to need to go and look at these scores again. So let's see if we can move this in here. Okay, let's move this into Excel. If it will let us, it should. So let's move this into Excel right here. And now we need to know what is our mean. Well, we can take a shortcut in Excel. We can say equals average, and then we can do all of these like that between those two. Why did it tell us? So to the average of F28 to, that's weird. It should tell us. All right, well, then let's just create a new table. Let's go 17, 63, no, 63. I think with the cutting and pasting, it's something weird. 90, 51, 78, 44, 87, 37, 72, 51, 59, 70, 59, 69, 70, 88, 69, 72, 90, 37, 50, 57. Okay, so these all, that matches, that matches, that matches, that matches. Looks like these all do in fact match. Yeah, okay, so let's try that again. Let's see if we can sum these this time. Sum, there's our sum. And then we can actually just say equals average. And then put our brackets. And then we can say the average, what is our average of all these, which is our mean, which is 62.25. Now, of course, if we divide this sum equals, what is that? That is G48, this number right here, and we divide it by 20, we're gonna get the same thing, okay? So we can either tell it, here's the formula in Excel, or we divide, remember, the total over n, like the total number of values to get our mean. So now we have our mean. Now, what else do we need? Let's go back to our worksheet here. So we did the mean minus the sample mean over the standard deviation. We don't have the standard deviation. We need our standard deviation. So let's take all of these. We're going to do our sum of our squares thing. So first, we're going to take the 17 minus, so that's going to equal this value, which is G28, 28 right here, minus wherever our mean is, which if we just go like this, let's actually just get out of this formula for a second. We just go like this and we just label this mean. Now we can't really do that. We'll call this mean 2 sample, okay? So now if this mean 2 sample, it doesn't like that. We'll call it the mean. No, that's fine. We'll just not label that because that seems to be temperamental today. All right, so this is equal to G28, 28 minus, what is this? This is H48, H48. So we're going to do all of those. Now we should go just fill down. That should just work. Fill down. Nope, didn't work. That's okay. Equal to G28, G29 minus the mean, which is the 48. H48. or minus G29 minus 62.25, or minus, yeah, we'll just say H48. So same thing, equals G30 minus H48 equals G31 minus H48. So we're just getting the difference, okay? So equals, what is that, G32 minus H48, like that, equals G33 minus H48 equals G34 minus H48 equals G35 minus H48 equals G36 minus H48, same thing, equals G37 minus H48, same thing, equals G38 minus H48, same thing, equals G39 minus H48 equals G40 minus H48 equals G41 minus H48 equals G42 minus H48 equals G43 minus H48 equals G44 minus H48 equals G45 minus H48 equals G46 minus H48 and equals G47 minus H48. So now we've taken in the difference, we're taking all the values minus the sample mean to get this column. Now, if you remember, we want to square these, okay? So we're going to square all these. This is going to be equal to H28 to the second power. Now, hopefully I can just tell it to square these all the way down. Let's see if this works. Yep, those are our squares. Now we can highlight this and we can make this all, I would just really stick with 2 decimals. Just makes it cleaner, easier to work with. So now we're going to come up with, we remember the sum of the squares. Okay. So we're going to take the sum of the squares and we're going to just tell it we want the sum. That's our sum. Now the next thing we need to figure out is our variance, and then we're going to figure out what our standard deviation is. So if you remember, when we were up here, we were looking at that. So we're going to take the standard deviation divided by, so if we come back up here just to walk you guys through it. So the variance is going to be equal to the total sum of the squares over n minus 1, because we're dealing with the sample. So that means we're going to take this and divide it by 19. So we'll take equals, and this is I48 divided by 19, n minus 1, because we had 20 values. 19.24, that's our variance, but then we need to get the square root. So this is going to be equals square root of, which is I49, which should be our standard deviation of 43.87, which makes sense. So this is our standard deviation, and this, of course, was our variance, okay? So now let's go back. Now I think we have all our stuff through our calculations. So let's go back. Let's look at that. Yeah, so we have the same steps. So it's going to be D is equal to our sample mean, which is our capital M, minus our original population mean over our standard deviation. So we have that. So for this next one, it's going to be equal to D is equal to what is our mean? 62.65. So that's 62.65. Was that six? Was it 25? I think it was 25. 62.25. Okay, so we'll go back. 62.25 minus our actual original standard deviation, our original mean rather, 72.43 from our population, divided by 43.87, because we had a higher 43.87, because we had different values. So what does that give us? 62.65. So for our Cohen's D, we'll just calculate that out. That is 62.25 minus 77.43 divided by 43.87. And we get D is going to be equal to, and that should really be lowercase. Word just keeps wanting to capitalize it. That should be equal to negative 0.34. And that's our Cohen's D, okay? So the next thing we're going to do is ETA is a measure of proportion. So note some formulas. Proportion of variance is equal to variability explained divided by total variability. So ETA squared is a measure of proportion of variance that can be expressed in a single formula based on the results of the test. So we're going to take n squared is equal to t2 squared divided by t squared plus degrees of freedom. So in this formula, t is the value of this test statistic, and the degrees of freedom is the degrees of freedom. In this example, t obtained is negative 3.126, and degrees of freedom is equal to 17. To find the variance, we square the standard deviation. Thus, in the ETA squared formula, we square the value of t to find its proportion of the variance. The proportion of the variance for this data in our first walkthrough is negative 3.26 squared plus 17 is equal to negative 3.216 plus 17, which is equal to 0.36. Therefore, we can say in this example, we conclude that 36% of the variability in social functioning, the D-dependent variable, can be explained by the fact that the participants were relatives who care for patients with OCD of the treatment. Now calculate the ETA squared from the previous section. So I believe we have our T obtained value, don't we? We go back up here. We do. We have the T obtained value, which is 3.57. So we're just going to take this and we're going to plug that back in to our calculation. Really that straightforward. So we're going to take our T obtained value and our degrees of freedom. So let's just put that in here. Now, it's not this. It was 3.57. It was positive, okay? 3.57. And our degrees of freedom were 19 because it was not, because it was 20. Therefore, we're going to take our formula, and it's going to be T squared, okay? So that's going to be 3.57, and that's going to be squared. And remember, PEMDAS, the orders of operations, divided by 3.57 squared plus squared plus 19. Now, if you do like double brackets with a scientific calculator that we can pull up online here, you're probably going to get that right. I think the problem comes up when you try to do it without a scientific calculator, or you try to just do it like by hand, like maybe like on your smartphone, iPhone, Android, etc. They tend to run into some issues. So let's pull up a scientific calculator and see if we can get this to come up right on the first shot here. Scientific calculator, and I'll show you guys that in just a second. Scientific calculator, like that. And let's move the scientific calculator over to the screen. And we had double brackets, 3.57 squared second power, divide like that. divided by two brackets, 3.57, let's go squared, plus 19. Now that should work. Yes, it does. And that is 0.40147. So you move the decimal over two places and you'd have 40.1. So if we go back here, this is going to be equal to 0.40, okay? Therefore, I'm just rounding, we can conclude that 40% of the participants of the variability in social functioning of the dependent variable can explain by the fact that participants were relatives who care for patients with OCD either with treatment. Then we have omega squared. So omega squared is also the variability explained by a treatment divided by total variability observed. The change in the formula of a proportion of variance 1 is subtracted from t squared in the numerator. Therefore, W2 is equal to t squared minus 1, t squared plus degrees of freedom. So subtracting 1 in the numerator reduces the estimate of effect size. Hence, omega squared will always give a smaller or more conservative estimate of effect size, making it less biased than ETA squared. Using the omega squared formula, the proportion of variance from the data in the first example is the following. W squared is equal to negative 3.216 minus 1, or negative 3.26 squared plus 17, which is 0.33. So we conclude that 33% of the variability in social functioning, the dependent variable, can explain by the fact that participants were relatives who care for patients with OCD treatment. And then what that is known as what we call a large effect. Now, if we wanted the same math, it's the same thing, except this time W squared. So we're going to take W squared is equal to plus, is equal to, so we're going to minus 1 in the numerator, and it's going to be the same in the denominator, okay? So we're going to take W squared, in this example, is going to be equal, to 3.57, and then we're going to square that. Let's make this a square. We're going to square that, and then we're going to subtract 1, so minus 1, and that's going to be our numerator, and then our denominator, of course, is going to be 3.57 squared again, plus our degrees of freedom, in this case was 19, okay? So now we're going to take this and put it into our scientific calculator here, and then we're going to have a different conclusion here for this other half. So let's maybe bring this down here, and not like that, and see what this looks like. So let's go like that, and let's go back to our scientific calculator and kind of like this. And we're going to say, remember, double brackets, always a great way to do it. 3.57 to the second power. And let's actually, and then go plus 1. No, minus 1. It's minus 1 divided by, double brackets again, 3.57 to the second power plus 19 bracket equals negative 0.36. So that went down a little bit, similar to the previous calculation that wasn't W squared. So 3.699, we'd round up, that'd be 0.37. So we go back here, and that would equals 0.37. Therefore, we conclude, because we move the decimal over two places, that 37% of the variability in social functioning of the dependent variable can be explained by the fact that participants were relatives who care for patients with OCD treatment. if you reference there's a table in our text, this would also be a large effect as well. So just some more definitions and things to talk about. Our next thing is, in a related sample, also called the dependent sample, participants are related. Participants can be related in one of two ways. They are observed in more than one group, which is your repeated measures design, or they are matched experimentally or naturally based on common characteristics or traits, a matched pairs design. Then we have the repeated measures design. The repeated measures design is a research design in which the same participants are observed in each treatment. Two types of repeated measures designs are the pre-post design and the within subjects design. The pre-post design is a type of repeated measures design in which researchers measure a dependent variable for participants before, pre, and after a post treatment. FYI, the two types of designs for selecting related samples are repeated measures and matched pairs designs. In a matched pairs design, participants are matched based on the characteristics that they share. Matched pairs can be obtained either experimentally or through natural occurrence. In a repeated measures design, the same participants are observed in each treatment. Two types of repeated measures designs are the pre-post and the within subject designs. Computing different scores prior to computing the test statistic reduces error by eliminating one possible source of error, thereby increasing the power of a hypothesis test. The degrees of freedom for the related samples t-test are equal to the number of different scores minus one, or degrees of freedom. This is your difference, okay? Two assumptions for a related samples t-test are normality and independence within groups. Some definitions. The within subjects design is a type of repeated measures design in which researchers observe the same participants across many treatments, but not necessarily before and after a treatment. The matched pairs design, also called the matched subjects design or matched samples design, is a research design in which participants are selected and then matched experimentally or naturally based on common characteristics or traits. The related samples t-test is a statistical procedure used to test hypotheses concerning two related samples selected from populations in which the variance in one or both of the populations is unknown. A different score is a score or value obtained by subtracting one score from another. In related samples t-test, different scores are obtained prior to computing the test statistic. For a t-test, the term error refers to any unexplained difference that cannot be attributed to or caused by having different treatments. The standard error of the mean is used to measure the error or unexplained differences in a statistical design. The estimated standard error for difference scores, or SM, is an estimate of the standard deviation of a sampling distribution of mean difference scores. It is an estimate of the standard error or standard distance that the mean difference scores deviate from the mean difference score stated in the null hypothesis. Example one. One area of focus in many areas of psychology and in education is on understanding and promoting reading among children and adults. Suppose we conduct a study with this area of focus testing if teacher supervision influences the time that elementary school children read. To test this, we stage 2 6-minute reading sessions and record the time in seconds that children spend reading in each session. In one session, the children read with a teacher present in the room. In another session, the same group of children read without a teacher present. The difference in time spent reading in the presence versus the absence of a teacher is recorded. Here is our table. That's what that looks like. So state one, you state the hypotheses. Because we are testing whether or not equal to a difference exists, the null hypothesis states that there is no mean difference, and the alternative hypothesis states that there is a mean difference. Therefore, the difference is that there's no mean difference in time spent reading in the presence versus absence of a teacher. The alternative hypothesis is not equal to 0. That means there is a mean difference in time spent reading in the presence versus the absence of a teacher. So first, we have the null and alternative hypotheses make statements about a population. We're going to set the criteria for a decision. We're going to use our alpha level. We keep using the level of significance for this test is 0.05. This is a two-tailed test and the mean difference between two related samples. The degrees of freedom for this test are 8 minus 1 because there's 8 participants. We locate 7 degrees of freedom in the far left column in the unit normal table, and it might say Appendix C in the posted PDF file. I believe it does. You move across to the column to find the critical values for a 0.05 proportion of tails. The critical values for this test are represented at plus or minus 3.65, and let's do a whiteboard example. Let's just put that right in there and do a whiteboard example. So what that's going to look like is something like this. We're looking again for the rejection regions in a two-tailed test. So if we whiteboard this, probably go ahead and erase some of this. Just waiting for my whiteboard. Okay, there we go. All right, so it's not chat. Whiteboard. I think you guys can all see that. Something's up with my whiteboard. Let's try that again. Whiteboard, like that. Okay. And let's erase all of this. Let's make the whiteboard a little bit bigger. What we're looking again for is that two-tailed test. Okay, so for our two-tailed test, we have our, again, this, and then our rejection region, which is right here, which of course is going to be your 2.365. That is our critical value. Critical value. And this other one is our critical value here. So this is negative, right? And this is positive, 2.365. Again, critical values. This is where we're going to reject. And then, of course, between we would retain, right? And then again, reject. And remember, it's not, if this is ever confusing, just to reiterate, it's always at the spot or further is where the rejection region starts. So it's never we're going to retain if we're at the spot. If we're at or beyond, that's where we're going to reject. And it's rare that I would hit right on that, but that's just, again, to reiterate for your own notes. Okay, so we will compare let's do a new screen share here so you can all see my Word document. So we will compare the value of the test statistic to the critical values. If the test statistic falls beyond either critical value, we just talked about that, there's less than a 5% chance that we would obtain the outcome if the null hypothesis were true. So we reject the null hypothesis, otherwise we retain the null hypothesis. So first we're going to compute the test statistic. We compute the mean variance and the standard deviation for the scores, compute, not computer. I don't know why it keeps doing that. I think it's just Word wanting to think for us here. The estimated standard error for the difference scores, and then compute the test statistic. So first, we're going to compute the mean variance and standard deviation for the difference, for the standard deviation of the scores. Keep in mind that the sign positive or negative, no matter what we compute, is standard deviation. So to compute the mean, sum the different scores and divide by the total number scores summed. So we want to look at that, which I believe I have an Excel file here. Just a second to see if I can pull that up. I believe I actually have that readily available here. Yeah, got it. Okay, so let's, yeah. So we do have that, so perfect. Okay. So first what we do is we are trying to find the mean difference for the sum of the difference divided by the n. So 120 divided by 8 is 15, but where do we get that from? Well, we took the present versus absent and they got the difference. So these are positive and negative numbers, and then I summed the difference, that's 120. That's where that came from. The next thing we're going to do is to compute the variance. We use a computational formula for sample variance, and we're going to find the sum of the squares divided by n, the end of the difference over 1. So we squared all of these values, okay? Squared all these values, and that's our sum of our squares right there, or the sum of the difference squared, okay? That's where that came from. So we're going to take the sum of the squares is 3,400 minus 120 squared equals 1,600. And then the standard deviation of 1,600 is 1,600 divided by 8 minus 1 is equal to 22.8, 22.57. So we took the sum of the squares, which is our sum. So this formula here, the sum of the squares difference minus sum of the squares squared minus 120 squared divided by 8 participants, okay, which is our n. So we took this minus that divided by our n, which was 8. So that's, or degrees of freedom, n minus 1. 8 minus 1 is 7. We got 22.58. That's just our 22.57. That's our variance. Now to compute the standard deviation, we take the square root of the variance, which is 15.12. Then to compute the estimated standard error for the difference of scores, we substitute 15.12 for the standard deviation and 8 for the difference. 15.12 divided by the square root of 8 is 5.35. Therefore, we compute the test statistic. We substitute 15 for the mean difference for 0, which is our difference of our mean. This is the value stated in the null hypothesis, and 5.35 for our standard error of the mean difference. So T obtained value, mean difference in our sample minus our mean difference in our population, 15 minus 0, which is 5.35. So what we're going to do is we're going to take 15 minus 0 and we're going to divide it by 5.35 and we get 2.804. Now that tells us our obtained value, okay? So we took this and we divided it by the standard error, right? The standard error mean difference. So mean population, mean sample minus mean population difference divided by the standard error of the mean difference is 2.804. So we're going to make a decision. We compare the obtained value to the critical value. Because 2.804 is greater than 2.365, the decision is to reject the null hypothesis. So now we do the same thing for this table. So I believe we have this table right here. Yes, we do. So again, we took the difference in the scores right here, and we squared them and we summed them. So we're going to take that same information and literally just plug it in right here. So what we're going to do is you have this right here, and let's just do our steps. So it's still 2.365, okay, because it's the same amount of 7 degrees of freedom is still 8, okay? So let's just take all of this and move this down here, okay, for our Word document. Okay, so we're going to take that. Nope, not what I wanted to do. We're going to take and state our hypothesis, kind of the same thing, same critical values. So we're just going to move our step 1 right down here in our worksheet. So now we got to start doing the math. Now we have all of it set up for us right here. So what I'm going to do is we'll take and we'll move this, but then we'll put everything in here so it makes sense, okay? Based on what our Excel file says. And then we'll do the T obtained value and everything before we make a decision. So we need to do all our steps here, but we need to fill that in so that it makes sense, okay? So first of all, the sum of the squares is, so that's 94. That's not 120 anymore. Okay, the sum of the difference in the scores. So that needs to be 94 divided by 8 for our first calculation here. So 94 divided by 8. So calculator, 94 divided by 8. That's going to be 11.75. Okay. So that's just our mean variance right here. We're doing this first step. And we need to keep going here because we need to, no, this is actually just our sum of the difference in the squares. So this is basically our mean. Okay. So we have our mean. That's great. Now we need our variance and then our standard deviation of the scores. So to compute the variance, we're going to do the sum of the squares, which we have, which is 2100. So that's going to be equals 2100 minus 94 squared, but we're still going to divide that by 8. So change this, and we're just calculating variance. So it'll still be 8 minus 1, so that'll still be 7. So 20. So let's go back to our scientific calculator. I believe we have right here, maybe. Scientific calculator. Okay, we'll move that over here. So we have our formula. We have our 2100 minus 94 squared. So let's do some double brackets here. Is that not showing? Here we go. 2100. So let's do double brackets. 2100 minus 94 squared go squared divided by 7, I believe. Yeah. No, divided by 8. So back here, divided by 8. That doesn't make sense. 100 minus 94 squared divided by 8. 94 squared, 94 squared, 836. Okay, 2100 minus 80 minus 94 squared. Okay, divided by 8 is negative 842. That's okay. Let's see. Yeah, negative 842. And then we're going to take that and we're going to divide that by 7, 8 minus 1, and we'll get a new number right here. That'll be our variance. And then we'll do our square root of variance. Because remember, it's a two-tailed test. So that's totally okay. So divided by 7 is negative 120.28. So that is right here. So that's going to be equal to negative 120.28. Makes sense. And then we'll take the square root. Oh, because it's a difference. So that's fine. It's a difference. That's why it's okay. So we're going to divide that. We're going to take the square root of 120.28. And that is going to be equal to, so let's take the square root of negative 120.28. Let's make sure that's making sense here. All right, so that was 2100. Oh, hang on. I think we need to go back up and look at this. So 2100. E squared minus Oh, e squared, oh, there's an extra minus. E2 squared. So oh, okay, that's why. Okay. So the reason that's not working is just checking the formulas here, pretty straightforward. So what we want to do is we're taking, before we divide it, we're taking the 94 squared and we're dividing that by 8, which is 1104.5, and that's actually being subtracted from the 2100. So it's literally 2100 minus, and then you want like some, I do like triple brackets here, 94 squared, okay, minus 8, and then divide it, no, not minus 8, divided by 8. That's what's being subtracted, okay, which is 999 with 999.5, which makes a lot more sense. And then we're going to do the square root of that. Okay, so that's actually right here. It's going to be 995.5, which is right. Which is we get to this, which is 995.5, and then we divide it by 7, and we're going to get a positive number right here. So then divided by 7 is 142.24, which is 142.24. And then we're going to take the square root of that, 142.24, 2.24. And then we're going to get whatever that is. So let's go back to our scientific calculator, and 142.21. Do we have that down? 141.21. So now we're going to take the square root of that. So square root of 142.21, and that is 11.92. So let's go back here, and that is going to be our standard deviation. So that's going to be 11.92. So we're going to substitute that. So this will be 11.92 divided by the square root of 8. So we'll go back to divided by the square root of 8. We're going to get 4.21 or 4.22. Call it 4.22, we'll round up. So this is equal to 4.22, which is, of course, our obtained value. That is our standard. That is our standard error of the mean at this point, 4.22. Then we want to compute the test statistic. We're going to substitute we're still going to substitute 15 no, we're going to substitute. Where's my Excel file? It's 94 divided by 8. This is not 120, 94 divided by 8. We're going to substitute 11.75. So we're going to substitute 11.75 for the standard difference in the area of score. So 11 points, because that was our mean, 11.75. And ND divided by, not there. Yeah, that's fine. Okay, and then we're going to take 11.75 minus 0 divided by the standard mean deviation, standard mean difference, which is the 4.22, and then we're going to get the critical value. So the critical value is 11.75 minus 0 divided by 4.22, which is 2.78. So in this case, because it was 2.365, it's going to be the same thing. We're going to reject the null hypothesis. So we're going to make our decision, which is up here. And we're going to reject it because it obtains it that it is greater than the critical value. Some more definitions. Estimation is a statistical procedure in which a sample statistic is used to estimate the value of an unknown population parameter. Two types of estimation are point estimation and interval estimation. Interval estimation is a statistical procedure in which a sample of data is used to find the interval or range of possible values within which a population parameter is likely to be contained. A confidence interval is the interval or range of possible values within which an unknown population parameter is likely to be obtained. A level of confidence is a probability or likelihood that an interval estimate will contain an unknown population parameter, for example, a population mean. The confidence limits or confidence boundaries are the upper and lower boundaries of a confidence interval given within a specified level of confidence. FYI, a point estimate is a sample mean or a sample mean difference. The sample mean is used to estimate the population mean. An interval mean is the interval range or range of values within which an unknown population is likely to be contained. The interval estimate is computed using the standard error of a sampling distribution. A population mean is estimated as a point estimate plus or minus an interval estimate. We use the estimation to learn more about an unknown population mean by identifying the confidence limits within which the true population mean is likely to be contained. Example 1, a common measure of intelligence is the intelligent quotient IQ test, in which scores in the general healthy population are normally distributed 100 plus or minus 15, mean plus standard deviation. That is our notation. Assume we selected a sample of 100 graduate students to identify if the IQ of these students was significantly different than that of the generally healthy adult population. We recorded a sample mean equal to 103. Let's find the 98% confidence interval for these data. So the standard error is the population standard deviation divided by the square root of the sample size. So we're going to take 15 divided by the square root of 100, which is 1.5. Now, where did we get that from? We got that from our standard deviation divided by the total number, because we had 100 students. So we happen to have this 100 is not the same. This is our mean, but because we had 100, which was like our n, that's why we divided that to get to 1.50. Next, you want to choose the level of confidence and find the critical values at that level of confidence. In this example, we want to find the 90% confidence interval, so we choose a 90% level of confidence. Remember, in a sampling distribution, 50% of sample means fall above the sample mean we selected and 50% fall below it. We're looking for a 90% of the sample means that surround the sample mean we selected, meaning that 45% of the sample means above and 45% below the sample mean we selected. This only leaves 5% of the sample means remaining in the upper and the lower tail. Remember, upper and lower tail, right and left of our rejection, where we have our rejection regions we were just drawing on the whiteboard earlier. To find the critical value, we look at the Z table in the unit normal table. And I believe that still may say Appendix C for you, but that is in the unit normal table. I did post that, the unit normal table. And we find the 0.0500 in column C. In the appendix, you'll see that 0.0500 falls between a Z-score of 1.64 and 1.65. The average of these two Z-scores is the Z-score associated with 5% towards the tails. Z is equal to 1.645. That's between the 1.64 and the 1.65 in your unit normal table. In our example, 1.645 is the cutoff for a 90% confidence interval, whereas where 45% of the data are above and 45% are below the mean. The remaining data are 10% of the data in the tails, which equates the critical value we choose to use a two-tailed test at a 0.10 alpha level, 5% in each tail. So what we're going to do is we're going to think about the estimation that corresponds to two different levels of significance. So we're going to compute the estimation formula to find the confidence limits for 90% level of confidence. Because we are estimating the mean in a single population with a known variance, we use the mean plus or minus z times the standard error formula. So we have all that. Z times standard deviation is 1.645 times 1.50 is 2.47. You add it to the sample mean to give you the upper confidence limit and subtract it to get the lower confidence limit. Therefore, 103 plus 2.47 is 105.47, and 103 minus 2.47 is 100.53. Therefore, we can estimate with a 90% confidence level that the mean IQ score in this population of graduate students is between 100.53 and 105.47. We are 90% confident that the population means fall within this range of IQ scores because 90% of all sample means we could have selected from this population fall within the range of the sample means we specified. Now, doing the following, using the same steps in the sample, do it on your own, showing your own work. So assume we have a sample of 120 graduate students and we want to see this generally different. Let's find the 90% confidence interval, and our mean is 110, which is our sample mean. So we can literally just follow the steps here, okay? So we're going to take step one and let's do step one as a group here, okay? So the first thing we're going to do is, here we go, step one. Compute the sample mean and the standard error, okay? So the sample mean is equal to, well, our standard error is equal to our standard deviation, which is the same, but our n is no longer 100, it's 120. So we're going to have a different standard error right here. So we're going to take 15 divided by the square root of 120, which will end up being a little bit different. So let's do that right here. Let's say 15 divided by the square root of 120 is equal to what? 1.369 or 1.37. So let's round. We'll put that here. That's equal to 1.37. Okay, so that's our first step. The next thing we're going to do is we are going to choose a level of confidence, but this is going to be identical because we want the same level of confidence. So our z-score is totally going to be the same, okay? And then we'll do the estimation formula because that's literally what we just found. So this is absolutely all the same. And then step three, we use the formula to find that. So we just plug in the different estimation formula. So that's pretty straightforward, but I'll move that all down here. However, this is no longer 1.50. This is 1.369 or 1.37. So this changes this, which changes all of this for upper and lower confidence limits. So 1.645 times 1.37, 1.645 times 1.37 is equal to 2.25. So we're going to add 2.25 for our upper and lower confidence limits and subtract it. Minus 2.25. So Our upper confidence limit would be, I believe, 105.25, but we'll do the calculator just to make sure. 105.25. And then our lower confidence limit, again, that's subtraction, same formula. So 103 minus 2.25 is equal to 100.75. Therefore, we can conclude that it's between 100.75 and 105.25 that 95% confident that the population means fall within this range of IQ scores, because 90% of all the sample means we could have selected from this population fall within this range of the mean samples we specified. All right, so some more things to think about. FYI, we use estimation to learn more about unknown population mean by identifying the confidence limits within which the true population mean is likely to be contained. The estimation formula for a t-test is used when we estimate the mean or the mean difference populations within an unknown variance. So the upper confidence limit is the largest possible value of the population parameter in a confidence interval with a specified level of confidence. The lower confidence limit is the smallest possible value of a population parameter in a confidence interval with a specified level of confidence. Just looking at what we have coming up here. Okay. So social functioning is the ability of an individual to interact or adapt in a normal or a usual way in social environments. This area of research is of interest to the behavioral researcher, particularly in medical or clinical settings, to those who study human development. Okay. In this study, we recorded relatives of patients with OCD that are healthy against those that are not healthy. So I feel like we just did all of this, but we'll walk through it again. In a sample of 80 participants, we recorded that mean is 62 and the standard deviation is 20.94. Here we find the confidence interval in these set of data. So first you compute the sample mean and estimated standard deviation divided by the square root of the sample size. So the standard error is equal to the standard deviation, which we have, divided by n. So 20.94 divided by 8, square root of 18 is 4.94. Next, we're going to choose level of confidence and find the critical values at that level of confidence. In this example, we want to find the 95% confidence interval. So we choose the 95% level of confidence. Remember, in a sampling distribution, 50% of the sample means fall above the sample mean that we selected. Referring to the unit normal table, we find that a 95% confidence corresponds to a two-tailed test. To find the critical value, again, unit normal table, appendix C, the degrees of freedom are 17 and minus 1, that's where we get 17. The upper critical value for interval estimates is t is equal to 2.110. Therefore, you compute the estimation formula to find the confidence limits for a 95% confidence interval, mean plus or minus the standard error. Because we are estimating the mean in a single population with an unknown variance, we use the estimation formula. T is equal to standard error 2.110 times 4.94 is 10.42. And then we add that to the sample mean, 62, to find the upper confidence limit. And then we do that to find the lower confidence limit. We subtract it. So the 95% confidence interval in this population is between a score of 51.58 and a score of 72.42 in the social functioning measure. We can estimate with 95% level of confidence that the mean social functioning of relatives with OCD using the SF36 survey is between 51.58 and 72.42 in the population. We're 95% confidence that this mean falls in the range because 95% of the sample means we could have selected from this population fall within the range of sample means we specified. Now to the same thing, mean is 60, standard deviation is 7.74. Make sure you have the right amount for your N, but I feel like you could just follow those rather than walk you through that because we just did that. So just follow the steps above. If you have questions, do reach out. Some more definitions. The levels of the factor symbolizes K are the number of groups or different ways in which independent or quasi-independent variables observed. FYI, analysis of variance measures the variance among two or more groups. Some definitions: analysis of variance, or ANOVA, is a statistical procedure used to test hypotheses for one or more factors concerning the variance among two or more groups. K is greater than 2, or the variance in one or more populations is known. In a one-way between subjects ANOVA, different participants are observed at each level of one factor. A one-way between subjects ANOVA is a statistical procedure used to test hypotheses for one factor with two or more levels concerning the variance among group means. This test is used when different participants are observed at each level of a factor and the variance in any one population is known. A between subjects design is a research design in which we select independent samples, meaning that the different participants are observed at each level of a factor. A one-way between subjects ANOVA can be used when samples are selected from one or more populations. For an ANOVA, K is the number of groups, N is the number of participants per group, and N, so we have our lowercase n and uppercase n, is the total number of participants in the study. There are two sources of variation in a one-way between subjects ANOVA, one way attributed to differences between groups and one associated with observing different participants in each group within groups. Definitions: between groups variation is a variation attributed to the mean differences between groups. A source of variation is any variation that can be measured in a study. In one way between subjects ANOVA, there are two sources of variation attributed to differences between group means and variation attributed to error. Within groups variation is a variation attributed to mean groups within each group. This source of variation cannot be attributed to or caused by having different groups and is therefore called error variation. An F distribution is a skewed distribution derived from a sampling of F ratios. The variances measured in an ANOVA test are computed as mean squares. A mean square is a variance. The two terms mean the same thing. They are synonyms. The formula for the test statistic, called the F statistic, is the variance between groups, or mean square between groups, MS between groups, divided by the variance within groups, or mean square within groups. Mean square within groups is more commonly called the mean square error. The formula for the test statistic is F obtained value is equal to mean square between groups, or variance between groups, divided by the mean square error, or variance within groups. FYI, the test for an ANOVA measures variance attributed to mean differences between groups divided by the variance attributed to error, mean square error. The definitions: the F statistic, or F obtained value, is the test statistic for an ANOVA. It is computed as the mean square or variance between groups divided by the mean square or variance within groups. Mean square has to do with, I'm not sharing, guys. Thought we were sharing this whole time. Okay, so we'll go back up here. Could have sworn we were sharing. So this really should be pretty straightforward, everybody. I would just pull up the Word document and scroll while I was talking. It's probably the best way to do it. But if you have questions, I definitely do ask. So we'll stop there just for a second. I think we were right about here. Yeah, let's just reiterate from about, I think we were right about here. We'll just start here in just a second and we'll keep going. All right, getting back to it, guys. And I would just scroll where when I was recording before on that Word document, because a lot of what I was walking you through is right on that Word document. A one way between subjects ANOVA, and I feel like the confidence intervals, I feel like that was pretty straightforward and everyone had a pretty good sense of those. So a one way ANOVA between subjects ANOVA is a statistical procedure used to test hypotheses for one factor when two or more levels concerning the variance among group means. This test is used when different participants are observed at each level of a factor and the variance in any one population is unknown. A between subjects design is a research design in which we select independent samples, meaning that different participants are observed at each level of a factor. A one way between subjects ANOVA can be used when samples are selected from one or more populations. For an ANOVA, K is the number of groups, N is the number of participants, and capital N is the total number of participants in a study. There are two sources of variation in the one way between subjects ANOVA. one way attributed to differences between groups, and one associated with observing different participants in each group within groups. Definitions. Between groups variation is variation attributed to mean differences between groups. A source of variation is any variation that can be attributed in the study. In the one way between subjects ANOVA, there are two sources of variation attributed to differences between group means and variation attributed to error. Within groups variation is the variation attributed to mean differences within each group. This source of variation cannot be attributed to or caused by having different groups and is therefore called error variation. An F distribution is a skewed distribution derived from a sampling distribution of F ratios. The variances measured in an ANOVA test are computed as mean squares. And I think we did talk about that. We can reiterate though. A mean square is a variance. The two terms mean the same thing. They're synonyms. The formula for the test statistic is called the F statistic, and it's the variance between groups, or mean square between groups, MSBG, divided by the variance within groups, or mean square within groups. Mean square within groups is more commonly called the mean square error. The formula for the test statistic is the F obtained value is equal to the mean square between groups or variance between groups. The mean square error or variance within groups. FYI, the test statistic for ANOVA measures the variance attributed to the mean differences between groups or mean square between groups divided by the variance attributed to the mean square error. Definitions. The F statistic or F obtained value is the test statistic for ANOVA. It is computed as the mean square or variance between groups divided by the mean square variance within groups. The mean square between groups is the variance attributed to the differences between group means. It is the mean numerator of the test statistic. The mean square error is, or mean square within groups, is the variance attributed to the differences within each group. It is the denominator of the test statistic. The degrees of freedom between groups, or degrees of freedom numerator, are the degrees of freedom associated with the variance of the group means in the numerator of the test statistic, and they're equal to the number of groups k minus 1. The variance in the numerator is attributed to differences between group means. The differences of freedom for this variance are called degrees of freedom numerator, or degrees of freedom between groups, BG. The degrees of freedom for between groups. For this variance in the number of groups k minus 1, degrees of freedom between groups is equal to k minus 1. The degrees of freedom error, or degrees of freedom within groups, or degrees of freedom within groups, or degrees of freedom denominator are the degrees of freedom associated with the error variance in the denominator. They are equal to the total sample size n minus the number of groups k. The variance for the denominator is attributed to error. The degrees of freedom for this variance are called the degrees of freedom error, degrees of freedom within groups, or degrees of freedom denominator. The degrees of freedom for this variance are the total sample size n minus the numerator of groups k. Degrees of freedom error is equal to n minus k. The reason for the reference to the numerator and denominator for degrees of freedom is that there are two sets of degrees of freedom, one for the variance placed in the numerator of the test statistic between groups, and one for the variance placed in the denominator of the test statistic, error variance. F obtained value is variance between groups and divided by variance within groups. So our degrees of freedom, k minus 1, n minus k. Let us calculate degrees of freedom hypothetical study. And I think we looked at this before. We had one factor type of class with 3 levels of psychology, psych, soc, and biology. K is equal to 3. We observed 5 students in each class, n equals 5, for a total of 15 participants in the study, n equals 15. Because n equals 15, the total degrees of freedom for this test should sum to 14, n minus 1 is 14. The degrees of freedom between groups in the numerator are k minus 1. Degree of freedom between groups, 3 minus 1 is 2. The degrees of freedom in the error of the degrees of freedom error in the denominator, n minus k. Degrees of freedom error is equal to 15 minus 3 equals 12. When we state the degrees of freedom for an ANOVA, we always state the degrees of freedom between two groups, then the degrees of freedom error. For this study, we have an ANOVA, 2 and 12 degrees of freedom. These degrees sum to 14, which equal n minus 1. The number of groups, k, and the sample size per group, n, and then the total n population, are used to compute degrees of freedom. So changing any one of the degrees of freedom will change the shape of the F distribution. As the value for k, n, or n increases, so too will the degrees of freedom. As the total degrees of freedom increase, the F distribution becomes less skewed, meaning that the tails of the F distribution pull closer to the y-axis. In terms of the critical values for an ANOVA, As degrees of freedom increase, the critical values get smaller. Hence, as the degrees of freedom increase, the power to detect effect also increases. To locate the critical values for ANOVA, we use an F table, which is in table C.3 in your unit normal table. And that lists the critical values at 0.05 and 0.01 level of significance. The values in boldface are a 0.01 level of significance, and then the ones not in boldface are 0.05. To use the table, look at the degrees of freedom numerator listed in the columns and the rows. The critical value is the entry found at the intersection of the 2 degrees of freedom for a one-way ANOVA with 2 and 12 degrees of freedom at a 0.05 level of significance. The critical value is 3.89. Keep in mind that the F distribution is positively skewed. It begins at 0 and is skewed toward positive values. So the critical value for all tests placed in the upper, so the critical value for all tests is placed in the upper tail. Negative outcomes are not possible in an F distribution. FYI, the null hypothesis for an ANOVA states that group means in the population do not vary. The alternative hypothesis states that group means in the population do vary. 4 assumptions for a one-way between subjects ANOVA are normality, random sampling, independence, and homogeneity of variance, like sameness of variance. The rejection region is always located in the upper tail of the F distribution, so the critical value is always positive. Now, this example we actually did in a previous lecture, but I'll walk you through it again. But we absolutely did this previously with this review. Employee turnover is a common concern among businesses and organizational psychologists because, hey, maybe you have a bad leader, because people usually quit their boss, not their job. Stress levels at a workplace are often cited as a key reason for increased employee turnover, which is the rate at which employees leave a company, thereby impacting costs needed to hire new employees. An example of one such study in this area of research, suppose we ask new employees at a company how long they feel they will remain with the company. All right, so we'll conclude here with this. In the last example, you'd certainly work on your own if you'd like to. Employee, well, you want to get points for this, at least for my folks over at Ferrum, Dominican students. Right now, this isn't worth points, but it's a worksheet you could use so you do well in the test. It might change that in the future. So employee turnover is a concern because sometimes the leader is not that great, okay? So an example, we asked new employees how long they'll remain with the company, and they said their level of stress was low, moderate, or high. And the time and years they said they would stay with the company are given below. The employees said they stay at the company among employees that rated the workplace as being high, moderate, or low stress environment. So we have that. So we start with our null hypothesis. Group means do not vary between groups in the employee population. Group means do vary between groups in the employee population. Step 2, set the criteria for the decision. The level of significance of this test is 0.05. The degrees of freedom between groups are K-1. Degrees of freedom between groups is 3 minus 1 is 2. The degrees of freedom are N minus K. Degrees of freedom error is 30 minus 3 is 27. So we find the critical value, we're looking at the 2 and 27 degrees of freedom, and we find this in the unit normal table, and the critical value is 3.35. That is the region of the upper tail for the rejection region for this test. We will compare the value of the test statistic with a critical value. If it's below the critical value, we're going to retain. If it's at or greater than 3.35, we reject the null hypothesis. Otherwise, we retain it. So we compute the test statistic. We compute the F statistic to determine the total variance attributed to the difference between group means relative to the variance attributed to error. Thus, the test statistic for the variance between groups, MS between groups, is divided by the variance error, MS error. F obtained value, MS between groups, divided by MS error, is 2 divided by 27, which is 0.074. Therefore, we retain the null hypothesis. So do the same steps, step 1, 2, and 3, with this data following the example. Make sure you're aware down here that your N, of course, is going to be 36, 12, 12, and 12. Here's your K, etc. So walk through those steps. We could certainly do that together, actually. So let's just do that. let's just walk through this one together just so you can have it. Okay, so first we're going to do this. Okay. All right. Group means do not vary. Set the criteria 0.05 degrees from or k minus 1. Well, what is k minus 1? Well, it's 3 minus 2 because we got 3 groups again. So that's pretty straightforward. So this one is your degrees of freedom between groups, like that. And then our next one is the degrees of freedom between error, n minus k. Well, this is different because we have 36. So it's 36 minus 36 minus 3 is equal to 33. Equal to 33. Therefore, we're going to find the critical value for 3 and 33 degrees, and it's not going to be 3.35. So we'll go back to our Word document here, and this is going to be 3 and 33 degrees of freedom. Well, where do those intersect? We need to go look at our F table. So we'll do that. Look at your unit normal table. I'll look at mine in my book here, and it should be something like freedom 3 and 33. Which is critical value is 2.89. So we're going to change that. Critical value is 2.89. So we're going to see if it's at or greater than 2.89. So we're going to take the same thing, step 3, the mean of thing between groups divided by mean square error. So it's going to be 3 divided by 33, and we're going to see if that's different than the 2.89. So we're going to say 3 divided by 33, which is equal to, grab our calculator here. Calculator, 3 divided by 33 is 0.09. That's positive, so that's 0.09. And in this case, we are going to retain the null hypothesis because it is much lower than the 2.89. So same thing, therefore we retain the null hypothesis. And that takes us to the end of that worksheet for review. I certainly hope that information was helpful. I hope you learned something, and I will see you in the next video.